Hello everyone, welcome to the third lecture of Spatial Statistics and Spatial Econometrics. My name is Gaurav Arora and we will today study what are called as spatial data structures. So, up until now we have seen some prominent examples of where spatial statistics is useful. We talked about how this dimension of location in determining statistics, this query of where added to how and what in traditional statistics brings to the table some really new analysis of how the data can be seen, what can be derived from the data, what can be learned from it. And we saw that the Economic Survey of India recently went ahead and used this dimension of location in understanding development parameters in India. We also looked at two components of spatial data, that is spatial heterogeneity and spatial dependence. So, spatial heterogeneity is more of a large scale global phenomenon, whereas spatial dependence, as we saw in the previous lecture, is a more local phenomenon where values nearby in space might be behaving similarly to other values in their locality compared to values that are farther away. So, today we are going to sort of follow up on what we had seen towards the end of the last lecture, which is this concept of remote sensing. That is, we are trying to, where are these spatial data coming from, what is the data generating process. And what we looked at was that there are these remote sensors placed on satellites that are going around throughout the year over over each location on Earth, and they are basically transmitting back data that we are then able to store, manipulate, analyze and then visualize for our purposes. But then when we actually have to store, manage or visualize these data, we need data structures, right. So, we need a structure to store these data, and that is the topic of today's lecture. So, I have on your screen two different types of data structures. One is called as the raster data, the second is called as the vector data. I am also characterizing on this slide that the raster data are continuous data, and we will talk about what this really means, and vector data are discrete data. This is a fundamentally distinct attribute between these two data sets, that is the raster data are continuous in nature and vector data are discrete in nature in the way they are stored, managed and visualized. And I want you to recall the definition that we sort of gave at the time when we talked about the geographic information system, and we said that this is a system which is designed to capture, store, manipulate, analyze, manage and visualize georeference data. So, data structures start right at the place where we have to store data, and then they have a fundamentally important role to play in how the data are managed, and then how we can present or visualize this data in our own work. So, let us get started. So, the first item is the raster data. A raster data contains of a matrix of cells or pixels organized as columns or rows, and there is a picture right in front of you where you can see that the raster data are organized as rows and columns. So, you have rows, and you have columns vertically. So, right, the rows are organized horizontally and the columns are organized vertically, right. And what happens is that for these rows and columns, you have these little cells that you can see on your screen, the cells that you can see on your screen. Each cell stores a unique digital value, okay. And this digital value, when put together in a matrix of rows and columns, allows us to visualize, okay. So, each pixel contains of information, right, in form of a digital value. So, now we are quantifying information from an image to a measure, right, and this digital value can represent multiple things. I mean, almost anything you can think of which can be sensed remotely or can be sort of put on a image which is spatially delineated. So I have examples here, you can have digital values that are temperatures, so it could be precipitation levels, it could be land use type. We have seen many examples of land use type till now. We had urban land use, agricultural land use, forest land use. And for each of these land uses, imagine if you had values 1, 2, 3, 4, 5, 6 and so on for different types of land uses. If you assign those values to different parts of this matrix in front of you, you can find a land use profile. For example, the Delhi NCR or the Chennai metropolitan region, Mumbai metropolitan region and so on and so forth. We also have aerosol concentration as an example. So pollution, that's another matter that we have discussed a bit about earlier. Those can also be stored as unique digital values in each pixel in these data, right? Now, raster data are the most fundamental form of, spatial data. Satellite imagery that is coming from sensors are raster data, right? If you take a picture on your phone from your own camera, if you display it on a computer screen and if you keep on zooming, the most fundamental or units that unbreakable units that you come across are pixels, right? That's the highest resolution at which you can look at that image, and each pixel has just one color. That color represents really a digital value, right? So raster data is something that we come across every day, all the time, as we look at how the world is captured on cameras of different kinds. So in the example here, if you look at the image, in the middle, that is a raster image, right? What's happening is that you have, if you keep zooming in, you will find the smallest units that from where you have a uniform understanding of each location will be a pixel. Each pixel will have a value, right? The value will represent here in this case, in this middle picture, middle image will be a color. For lighter colors, you will have some values, you will have, let's say, values that will range from 0 to 5. For slightly darker colors, you may have values which range from 5 to 10. And then for these colors where you have darker formations, you might have values ranging from 10 to 20, right? So, and this, scattered across space provides us a pictorial understanding of the real world. The third image is also quite similar. So, you have darker regions which can have higher values, or even the values can be reversed. So, the darker regions can have lower values, the lighter regions can have higher values, and they can represent different things. In the last image, what you are looking at is elevation on ground, right? So, darker images are where you have higher elevation, so you have ridges and hills on ground, and the lighter regions are where you have plains, right? So, they are all stored as unique digital values coming together to be seen as a raster image. The second form of spatial data structure is called as the vector data. So, vector data is a spatial or pictorial representation of the real world using points, lines and polygons. So, now you are basically taking the original pictorial image of the real world scenario that is of interest, and then you are converting it into structures like lines, polygons and points, and when you visualize those in that format, what you get is a vector data. So, vector data obviously is a data structure that is used to store spatial information that we have talked about earlier, and the data is stored in vector models with discrete boundaries like districts, country boundaries, blocks, agroecological zones, special economic zones, coastal boundaries and so on and so forth, right. So, if you are storing data in predetermined administrative lattices, for example, districts in India or at taluk level or at village level, then the kind of data set that we look at is called as the vector data, right. Here you do not have information merely stored in square cells that are delineated by rows and columns, right. You have irregular boundaries, which could be coastal regions, which could be different districts and so on and so forth. But this type of storage of information is useful because ultimately when, for example, for public policy, for governance, usually the policies are sort of implemented at the district level or at the taluk level or at the village level or a local municipality level. And so if you want to study spatial impacts, that is the location, location understanding, location-wise understanding of how policies, let's say education policies, schools impact welfare of local communities, then we better, learn how to study, how to sort of visualize vector data or to work with data which is in vector format. So the image here that you look at is converting a real world, data structure, which is, let's say, a raster data structure on your left, which is nothing but an image taken from a phone, from a satellite sensor, something. So it's a remotely sensed image. It has a region A, a region B, and a region C. What it looks to me is that region A seems to be some kind of an agricultural area. Region C, which is a line, looks like a road, right? And B, which is a larger dot, maybe looks like a pond, right? So there are these three features in this region that we have received in the original real world data format. And now we are going to convert it to a vector data format. So what is being done? You can see that first of all you have a coordinate system, right? So you have an origin and then you have a coordinate system where you have the x axis sort of broken down into discrete steps. So discrete steps of 1 to 2 to 3 to 4 and 5. And the vertical axis sort of, that is the y axis, is also similarly broken down into discrete steps, right. Like we said, vector data are discrete data. So we have these discrete steps in which the x, y, the two-dimensional space is broken down, right. When we do that, we get these points when we join all the sort of grid cells that we have created as discrete steps, we get these points on on the xy plane, right. And we are used to sort of understanding each point will have a x comma y coordinate, right. And if you recall, when we look at these coordinates, we are basically using the GCS system of creating georeferencing and creating a geo-coordinate system, right. Something that we have studied earlier. I would sort of motivate you to go back and look at it to understand how these coordinates will come about for a real world data set on land, right. Once we create these points, what we do is then we sort of discretize the space that we have as in circular form into discrete points which touch upon different regions in in my study area. So I get my circular sort of semicircle a representation of region A is now a polygon with 1, 2, 3, 4, 5, 6, 7 vertices, right. Similarly, this road, which was a curvy road, when it comes to the vector data format, it is a line with 1, 2, 3 and 4 vertices, right. And that point B simply reduces to a point coordinate B, right. That point coordinate, which will be basically the center of mass of this point B. Okay. So let us move forward. And now what I am showing you is a contrast of a real world when stored as raster image or when stored as a vector data or a vector image, right. So what you see, first of all, now the real world is in 3 dimensions, right. So you have a 3D representation of the real world, which is unlike our previous 2 examples, right. So what's happening here is that you have a x axis and a y axis, right, which is giving you the domain of land in a region that is being captured in the image that we are looking at. What we are also seeing is height of trees, the height of this house, little house on our image, and there is there is a differential that we can see of heights between these different objects, so between different trees and between the house and other objects in the picture. So when you look at the raster format or the raster understanding of it, what you see is a pixelated or a cell like format created with rows and columns, right. So again, you have these rows, you have columns, and what you're doing is that you're using you're giving a value to each cell to represent what's happening in the real world. So wherever you have R, you're giving a value R, that's where you see a river. Okay? These are cells which are representing the river in my data set, right, in my real world data set. Okay? And then you have these P's, which is a cluster of trees which are near the river, and these S values which are a cluster of trees away from the river, right. And then you have a house which is one cell on the picture, right. So that's the raster, representation of the real world. When we come to the vector representation, very interestingly, the river is reduced to a line, just like a road in the previous example. The river is reduced to a line. Once again, you have an x and y axis, you have a coordinate system that you're working with, and you have a gridded format that you create with discrete steps 1, 2, 3, 4, 5, both on x axis and y axis. And through these gridded points, you simply create a data structure where you reduce the curvy looking sort of river into a line with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 vertices, right. The house is reduced to a point, and the two clusters of these wilderness areas, which are cluster of trees, are now sort of reduced to polygons with different shapes representing the clustering sort of arrangement in space, and then also representing the location in the sense the cluster of trees P denoted by P are nearer to the river, that is on the river banks, and then S is away from the river. Okay? So, having now understood in detail how a raster data format works versus a vector data format, we will now quickly go over some of the applications that we come across, right, as in raster as well as the vector format. The examples that we have seen previously will also apply to this particular classification when we look at applications of remotely sensed data set or spatially delineated data set in raster format as well as in the vector format. So, what you see here is an image of the Arctic, more particularly the Arctic ice, and you see that between two seasons, that is the winter and the summer, you can see the difference in the size of the Arctic ice in April 2021, right. So, you can visualize how the ice structure, the ice mass shrinks and expands between these two seasons, and this is done using this continuous format where each cell in the image is containing a digital value. When that's happening, what happens around in winter, you have a certain value, let us say W, for all these pixels that I am drawing on the Arctic ice. That's the way our raster data are organized, right. When you overlay these pixels, right, when you overlay these pixels for for the summer season, what happens is that many of these locations turn from white to blue, and that means the ice has melted in that region, right. So, you are able to study the change in ice mass by looking at the raster representation of the data. Similarly, this is the Amazon. So, this is deforestation in the Amazon. You are looking at images that are ranging from year 2000 to year 2005 and year 2012. Everywhere you see that you have this expansion of the brown color in the raster format on raster pixels. You have basically replaced a green pixel which was the Amazonian forest to some kind of a development. It could be an agricultural land, it could be a road, and so on and so forth. So what you see here is an intensification of deforestation through time in a region, in a particular region, in Amazon, in the Amazon rainforest. This is another image which is also using raster data. On this image you have categories like always crop, always grass. So you have grasslands, you have croplands, they are existing besides each other. And among these are very interesting dynamics are grassland to cropland conversion. So if you are trying to understand decisions as to when or where exactly conversion decisions happen, this image tells you that the decision to convert happens as islands in large cropland tracts, right. So you have large grassland tracts, you don't see too many reds there, right. So the reds appear over time on regions which are yellow or in between within those regions which are yellow. That means that you are looking at conversions happening in a region where the land is already cropland, in the near locality, right. This can happen due to many reasons. You have markets which are more matured, you have more agricultural services. For example, you can rent agricultural machinery like tractors. You have services like insurance provision, you have credit, you have banks, etc., right. So if you have a very sort of a cropland sort of intense region, there is already an infrastructure. There are highways, there are transportation, infrastructure, there are mandis. So there is this infrastructure which sort of incentivizes, let's say landowners or farmers to then convert their land towards cropland, in regions which are already under, highly cropped areas. I think this is the last example. Now this is where the raster image is at. So there is a lot of application of machine learning on raster data and in identifying land use changes. This is just an example where a study is trying to sort of identify different types of land uses in the Andaman region of India. You can look at it if you are interested. So finally, I want to sort of go over some of the applications of vector data. So just like I had said earlier, vector data are stored as points, lines, or polygons. One of the most popular or prominent sort of applications or uses of vector data is in storing weather data. So weather data are stored on weather stations or in gridded format like you're seeing on the screen here. So you have these points placed equidistantly from each other along both x-axis and y-axis, right. This is the region of Uttar Pradesh, and what you are looking at is that each point in space has a daily record of minimum temperature, maximum temperature, precipitation, and so on and so forth. So the data are stored at these point locations. This is a storage mechanism, right. It also allows us to sort of visualize how the data would look like only through what the value that is attributable to these points on the map in front of you. Similarly, you have a groundwater monitoring network of the Central Groundwater Board and the Uttar Pradesh Groundwater Board here, and each dot is nothing but a monitoring well that is owned by the Groundwater Monitoring Agency, right. And you can see how they are distributed in space. All these locations are used to monitor what is the level of groundwater at any point of time that is in interest of the agency, right. So the agency can walk up to one particular well, monitor what's the level, and then come back later and figure out what's the level. So if you see water level going down, you have a indication of depletion, right. So such data sets are also vector data, right. I talked about administrative boundaries. So here is a block level assessment of Uttar Pradesh, again in terms of groundwater levels, and the greens here are regions which are safe in terms of groundwater depletion. The yellows are somewhat in worse situation, they are semi-critical. The oranges are are in trouble, and the reds are overexploited. So, so you see here on the western Uttar Pradesh side, which is closer to the national capital region, you have a lot more red, that is overexploited regions than others. That does not mean that they are all overexploited. You also have green regions around the NCR, which suggests that there is quite a bit variation in how groundwater dynamics works. And these data are recent data, they are 2017 data, so they are not ancient data or something. Here you see again the line format of vector data being used to visualize the national highway network of India. So, all the brown sort of lines that you see on this map are nothing but vector representations, vector storage of spatially delineated road national highway network in India. Okay. So, I want to sort of take you to some of the existing popular data sources of both raster and vector data. So, these data sets that I have been showing you over time, they are all, most of them are freely available online, and I am providing you some of the sources here. As a next step, what we will do is we will actually go over some of the data, and we will do some exercises to understand and how we can use this data, how we can bring this information to our own analysis. If you are researchers, you're working in policy, you're working in consulting, or you want to sort of explore some of those domains, then these data sets, the land use data set of the US Department of Agriculture, the rainfall and precipitation data set of the climate research unit of University of East Anglia, a version of which we saw for Uttar Pradesh a while ago. There are these free GIS data, there is the nighttime imagery, aerosol optical depth, which is a representation of air pollution. These are provisioned by NASA, and it's freely available at worldview.earthdata.nasa.gov. There is also Indian data, which is made available by Indian agencies. The most interesting of those, which is actually interesting to me, is the Indian Space Research Organization's Bhuvan portal. We will look at this data in some detail. It has many interesting features. And then there is India Night Lights data, which we saw during the starting sort of beginning of this course, where I showed you data on night lights and how they are changing over time in India. It is also a part of this data set is also sort of used to sort of delineate the economic development metrics for the Economic Survey of India. Okay. So, as a next step, we are going to do a short hands-on exercise with two of these data sets, so that we can see that we can actually work with these data sets. They are not really abstract entities, they are very much usable as available. Okay. So, we are looking at on your screen, we are looking at the Bhuvan land use land cover data set, the URL of which was pointed out, which I pointed out to you on the slide. So, here what you see on the right is a map of India. We see a layer which is overlaid here, which is the national highways, which are in brown lines, which is a vector format. And then we have these state names within India, and then outside India we have different countries which are also delineated here. So, when we start working with these data, the first thing that we need to do is we need to select a theme on which we want to analyze the data. So, the first theme you look at is land use land cover, which is 2005-06, land use land cover 2011-12, land use land cover 2015-16. So, you have these data layers for different years available for direct visualization on the website of the Bhuvan data set, right. You have also other interesting land use types, which is, let us say, land degradation. What is the status of land degradation? What is the urban land use status, wasteland, glacial lakes, flood hazards, so on and so forth. So, you should explore all these types at your disposal, right. I am going to go with the first one, which is land use land cover 2005-06. Once I click this, I get a select geography option, when I go ahead and try to select, what I get is different states in India. Because we have been looking at Uttar Pradesh, some examples, I am going to go and look at Uttar Pradesh. So, I select Uttar Pradesh as the geography of interest, and then I click on view. Once I click on view, on the right, this website directly points to land use in Uttar Pradesh, that I am looking at, right. This is for the year 2005-06. When we say 2005-06, it is the cropping calendar of India. That starts right at the time the monsoon comes, that is May of every year, right, May or June of every year, and then goes the next year, that is 2006, just before the monsoon, let us say till April of 2006. So, May 2005 to April 2006 is what is called as 2005-06. Okay. And what you see right away when you click view, you see a legend of different colors, different digital values on this map and what they represent. So, first of all, this map of India is really a raster format, right. So, it is a continuous data structure, right. It is a pixelated data structure, and for every pixel on my image, I have a value which is represented by a unique color, right. If I have two pixels which are side by side, have the same color, that basically means you have a similar type of land use going on in contiguity in that region, right. If you have a jump in colors between two pixels, you have some kind of a boundary or a discrete jump in the land use type, that is urban to rural, or agricultural. So, if you have a urban or agricultural frontier, then you have these jumps between red and yellows, right, given this legend. So, yellows are obviously, so you have reds and browns which are urbans, built up areas, the yellows are agricultural lands, the greens are forests, you also have grass, there are other kinds, there is barren land, there are wetlands, there are water bodies and so on and so forth. Okay. So, this is the legend. If we click on statistics, we will get a nice pie chart of what is the breakup of land use type in 2005 and 6 in Uttar Pradesh. These types of pie charts are what you are used to, right. If you are given data of what is the percentage of agricultural land in UP, urban land in UP, wasteland in UP, water bodies in UP, forest area in UP, and so on and so forth, you can create a pie chart on Excel, right. I am sure all of you are aware of it, and it is quite straightforward. What is interesting is that we are creating this pie chart from an image in this particular case, right. So, now we are able to visualize that the data that we are used to working with as data scientists or as applied statisticians, as econometricians on a comma separated value format, CSV format in an Excel sheet, can indeed be basically mapped to an image, and the data that we see on an image can be then mapped to the CSV format or other similar formats, right. That is interesting. What you also see is area in square kilometers. We can go one step further, we can click on analysis, and here what it says is you can draw a AOI and analyze. So, I am going to click draw AOI. So, we click on draw AOI, you can see my pointer. AOI means area of interest. We click here and then we go to the map, and I go to the western UP region which is adjoining the NCR, and I will draw a small area of interest which is, let us say, near Noida on the east of Delhi, right. So, I am going to click analyze, come back and click analyze, and what you see here is that my AOI that I had drawn on the image now appears on this map, and I have statistics for the area of interest that I have drawn on my image, right. So, you can look at an entire state, but you can actually then go to a local region of interest, which as a researcher, as someone who is just curious, wants to know, and we have now come to a region which is 62.85% urban land, right. We also have quite a bit of cropland here, which is, let us say, 20%, which is 18.9%. We have fallow land, we have grasslands, we have lakes, ponds, river, we have inland wetlands. So, there is a very diverse kind of a land use even in that local, in this local area of interest that we are studying here. As a next step, we can move to what is called as the metadata. So, the metadata are the ones which contain all necessary information that you should know about this data, including its data generating process, what is the level of accuracy. If you are using these data, you must cite these data. How should you cite these data? If you have an issue with this data, whom should you contact, right? If you have queries about these data, whom should you contact, right? So, let us look at it. So, there is data identification information, name of the data set, what is the theme, the keywords, access constraints, right, use constraints, and so on and so forth. There is contact information, just like I said. There is geographic location, right. So, we have a GCS, a geographic coordinate system. Remember, we have studied GCS in our lecture, in lecture 2, right. We have coverage, which tells us what are the extreme x, y coordinates on upper left, on upper right, lower right, and lower left. So, in this AOI, upper left, upper left, upper right, lower right, and then lower left. So, it is giving me the x, y coordinates that encompass the area of interest, right. Then we have citation. So, if you are using these data, this is how we cite these data, right. So, we must be aware of this. One very interesting data quality parameter that metadata provides, that is something that we should document whenever we are using these data, is on accuracy, right. It says overall accuracy of different LU/LC classes vary from 79% like agro horticulture. So, whenever we see a agricultural classification, it is true only 79% of 100 times, right. So, 79 of 100 times we are sure, we are confident that we have that class, but for remaining 21 times it could be some other class. So, there is some error in these data, right. So, we should be very careful about these, and we will study how to articulate these errors analytically. And then we have 97% accuracy for water bodies. So, we are doing a very good job with articulating where the water bodies are. Finally, I want to look at this overlay function on this website. Here, what you can see very interestingly is that you can overlay administrative units layers like taluks. So, you can study the Uttar Pradesh region at a much finer scale, that is taluks. You can move to districts. So, you can see districts are larger than taluks. So, taluks are more finer resolution administrative units, right. So, that is about it. I would like for you to look at these data, work with these data, play around a little bit. We will do a little exercise in the next lecture. I want you to sort of go and look at the Guwahati region and look at the Guwahati metropolitan area, draw area of interest, and analyze land use types. Look at the metadata and then maybe overlay a few features, right. And we will sort of do that again in the next lecture along with Cropscape, that is another publicly available freely downloadable data set we will see the functionalities for. Thank you.